Hey everyone, and welcome back. Today, we're looking at systems of linear equations, a key HL-only topic. We'll cover 2x2 systems, which might feel familiar, and 3x3 systems, which you'll definitely encounter, and the systematic ways to solve them. Let's start with two equations and two unknowns, like x and y. Remember, graphically, each equation is a line. Solving the system means finding where they intersect. There are three possibilities. First off, one intersection point, if a unique solution, xy, exists. Then, if the lines are parallel, there is no intersection, so there is no solution. And lastly, if the two lines are actually the same line, then there are infinite intersection points, so we have infinitely many solutions. Now, how do we find that solution algebraically? Let's revisit two methods that you've likely seen before. First up, substitution. The idea is to isolate one variable in one equation and substitute its expression into the other equation. For example, if we have 2x plus y is equal to 5 and x minus y is equal to 1, then we isolate a variable. From equation 1, it's easy to get y is equal to 5 minus 2x. Then we substitute that into the other equation, so we get x minus quantity 5 minus 2x is equal to 1. Then we solve the resulting single variable equation, x minus 5 plus 2x equal to 1, so 3x is equal to 6, so x is equal to 2. And finally, we substitute the found value back into either original equations, or the isolated expression, to find the other variable. Using y is equal to 5 minus 2x, we get y is equal to 5 minus 2 times 2 is equal to 5 minus 4 is equals to 1. So, the unique solution is 2, 1. X is equal to 2, y is equal to 1. Substitution is great when it's easy to isolate a variable. The next method is elimination. Here, the goal is to add or subtract the equations, possibly after multiplying them by constants, to eliminate one variable entirely. If we keep the same example system, 2x plus y is equal to 5 and x minus y is equal to 1, first, we align the equations and we see if adding or subtracting might cancel a variable. Here, notice the plus y in equation 1 and negative y in equation 2. If we add the equations, the y terms will cancel out. Step 2 is to perform the addition/subtraction. Here we have 2x plus y plus quantity x minus y is equal to 5 plus 1, which means 3x equal to 6. Then we solve for the remaining variable, which gives us x equal to 2, as we saw previously. We substitute this value back into the original equation, and we get y is equal to 1. So again, we get the solution 2, 1, x equal to 2, y is equal to 1. But sometimes, you might need to multiply one or both equations by a number first to make the coefficients match up for elimination. Now, let's step it up to three equations with three variables, x, y, and z. Geometrically, each equation is a plane in 3D space. We're looking for the point where all three planes intersect. The possibilities are still the same three, more or less. First off, we can have a single point with a unique solution. Or we might have no points in common, and thus no solution. For example, if our planes are parallel, or the planes intersect one another like a triangular prism. Or we can have intersection along a line or an entire plane, which means we have infinitely many solutions. While we can technically solve them by substitution or elimination, it gets messy fast. This is where Gaussian elimination comes in. It's like a systematic version of eliminations, which is perfect for calculators and computers, but also useful by hand. Instead of rewriting equations over and over, we use a sort of shorthand notation, often called an augmented matrix, but think of it just as a table storing the coefficients and constants. The goal is to manipulate this table using specific row operations, which are equivalent to the steps we take in elimination. We can swap two rows, which is like swapping two equations in elimination. We can multiply a row by a non-zero constant, which we would already be doing. Or we can add a multiple of one row to another row, which is adding a multiple of one equation to another. We use these operations strategically to get the table into what we call row echelon form. This means getting zeros in the bottom left corner, forming a sort of staircase pattern. Why? Because this form makes the system easy to solve. The last row will often give you the value of z directly, or tell you if there's no solution, like if you get 0, 0, 0, and 5, which means 0 is equal to 5, which is obviously impossible. Then you use that value in the second to last row to find y. This is called back substitution. And finally, we use y and z in the first row to find x. Sometimes you might end up with a row of all zeros. This means one equation was redundant, dependent on the others, and signals infinitely many solutions. In that case, we call z a free variable and express it in terms of a parameter, typically t. We can then still back substitute, but we will get an answer in terms of a parameter. Gaussian elimination, also known as row reduction or Gauss-Jordan elimination, is the standard procedure for systems of 3 or more equations in IBHL. It seems procedural, and it is, but it guarantees you'll find the solution, or lack thereof, systematically. One quick application. If you want to find the equation of a parabola, y is equal to ax squared plus bx plus c, through 3 given points, x1, y1, x2, y2, and x3, y3, we can plug each point in, which gives us 3 linear equations in terms of the coefficients, a, b, and c. You then solve this 3x3 system for a, b, c using Gaussian elimination. So to recap, for 2x2 systems, substitution and elimination are your go-to methods. For 3x3 systems and larger, Gaussian elimination provides a systematic approach. You need to understand the row operations, the goal, which is to get the matrix in row echelon form, and how to interpret the final result to determine if there is a unique solution or no solution or infinitely many solutions. Practice these methods, especially Gaussian elimination, until they feel comfortable. And that's it for systems of linear equations.